Okay, okay. We will continue. See, we have been discussing stability at small angle under intact condition, that is what we call initial stability, which is same as so we will continue this discussion. See, today I am going to talk about effect of free surface. Now, it's something like this, that all of us have experienced that if you want to carry a container with water in it with a lot of surface, for example the chiller tray, when the refrigerator chiller tray gets filled up, you want to carry, it's difficult to balance, it has a tendency to kind of spill over. Okay, you will also see that most of our designs of the water containers, the one that the ladies carry, villages and all, are all actually with very narrow neck. It is not only for carrying, but also for the fact that it has got a very small free surface. See, when you see this village ladies carrying, it's not only for carrying purpose, but always the mouth is narrowed down whenever you are carrying liquid. When you cannot do that, you will see the fishermen, when the milkman, when they go, they will actually put some kind of a hay inside. Again, that is for damping the liquid, so that the milk doesn't spill over. The entire concept of this all is that you should want to reduce the free surface. Means free surface here means the surface which is actually the liquid is here and water air is here. This is an interface of liquid and air. First of all, okay, before I go, let me define what is a free surface, because this comes very many times. Actually, free surface will imply interface of water and air. And I show it this way, this is water and this is air, the fish here and this thing here. See, this is why it is free surface, because it is free to move as you spill. It is actually, as you tilt it, it always stays horizontal. Now, this has a large effect on stability of initial stability of a ship, and why it is more, first of all, it has an effect. Secondly, why are we bothered? Now, you see, in almost all ships, you will be carrying some form of liquid. Even if it is a dry cargo vessel, it will have a fuel tank. Okay. Now, fuel tank, you may say, I am going to fill up the tank, but as you travel along, you are consuming fuel. So, there will be a time when the fuel will come down to some level. So, therefore, free surface existence on a ship is very much there. It is unavoidable. Now, it turns out that this free surface tends to reduce stability. If it was the other way around, like if presence of free surface of improved stability, we probably would not have been bothered. But presence of free surface causes a reduction, that is, makes it unsafe. So, obviously, we have to find out how unsafe it is, or along with the free surface, we must design the ship to be safe. This is exactly what is meant by free surface effect. We will see that there is a reduction of the metacentric height. How it happens or why it happens? Now, let us draw one. Keep some other pictures. See, ordinarily what has happened that we have seen earlier, that supposing I have got a center of gravity here, let me call this to be here for now G0, original G. I have a center of buoyancy here, initially somewhere, let me call it to be B. Now as the ship has tilted, once again this is supposed to be a small angle, okay, this is theta. I mean, we are dealing small angle, but I am showing large angle here. We know what has happened, that this B has got shifted here. It has not raised up, but it has got shifted here to some position B1. And then we had got this normal drawn, which has hit here. And this is my M. This is what we know. And obviously what happened, the weight was acting through this line. And this was my ZZ. This is my writing lever, that we have known. What changes would happen if there is a tank with a free surface? Let us say that now there is a tank here. It has got a liquid filled up to this much. See, we can see what happens here, that as the ship tilts, this liquid surface is also going to tilt, so it is going to also become like this. Again, remember that it is a small angle we are telling. Therefore, I mean, we are not. You may say why it is not hitting here, etc. But we cannot consider those cases because we are thinking of only 1 degree tilt. Just for drawing, I am showing that. So essentially, it is, even though it is a very small tank, even though the liquid is very small height, still it tilts. Okay, it is not that it, and it has no relation whether it is 80% filled or 20% filled. It, as long as there is a free surface, it is tilting, and this tilt angle we are considering is a very small angle theta. Therefore, it will tilt without hitting the top or whatever. I want to make it clear because many a times in the drawing there can be question coming, supposing it tilts too large like this, what happens? We are not talking of that possibility, we are talking of possibility at very small angle. Now what happens? See, if supposing this happens, now liquid here effectively has shifted down that side, as if you have again taken this piece and put, but earlier when we have taken this and put here, it was the buoyancy that got changed. But here what happened, this amount of liquid which is actually acting through this point, the weight of this, let us say there is a center of gravity G, this through G there was a liquid weight acting, as if I have removed that, the weight means I have put a weight like this and added here. See, I have cut that weight, therefore I have removed that much of weight. See, weight is acting downwards, so removal of weight will be acting upwards. How much is this for vector? Let us say it is small w. Let me call it right now small w. Okay. Now, what is the effect of that? You see, does it cause a change of B? No. B is basically centered of the underwater volume, this line. B is actually centered of the ship under the line W1 L1. So B does not change. So this is not changing. What is changing therefore is center of gravity, because you have shifted some weight from here to here. So the G here now therefore has shifted down to a distance here, somewhere here, to G1. Now our question is, how much is GG1? You see, now G is shifted here, therefore now the force is acting through this, and my writing lever is now only this much. But if I call this to be nu z, we can show this arrow, or if I draw this, say upward here, we will find out that the writing lever is equal to this point. I will come back to that. This becomes my again force is now, see, the G was here, so force was acting through this, buoyancy was acting up through this earlier, and I had ZZ is this much, writing lever, which was equal to GM into theta, GM into sine theta or GM into theta. But now, not the buoyancy, but center of gravity has shifted. Again, it is a small change, theta is small, so shift is only in the horizontal direction, not vertical. G has only shifted this direction. G has come down to G1. It has not shifted vertically. Why? Because this is very small, the angle is very small. So G to G1, there is no vertical shift. You see, it is like I had a weight here G, acting through this. I have added a weight here to G1. So this much of couple I have provided. That would have caused my center of gravity to shift. That has caused my G to shift to this much. We will have to figure it out that. But the question is that if it has shifted here, you see this distance becomes my righting lever because my weight now acts through this. In reality, this is my new center of gravity at that particular instant. So weight acts to this. So if I extend that, obviously this small line, because it becomes always small here, this becomes equal to this, or this line is my basically the righting lever, which I will come back to this afterwards, that how the formula comes to. So we understand first of all that there appears to be a reduction in the righting lever. See, earlier it was so much, now it is less. Okay, so there is a reduction in the righting lever. First, let us find out how much is the reduction. Okay, and then we can find out from the term of metacentric height. So we will be requiring this diagram again, perhaps. So I will try to work it here as whatever. See, how much is W? W is the weight of the liquid of this volume. Now let us say that this particular tank width is B. Remember, this is a cross section, so it is having a certain length. Okay, so this W is going to be integration of the area over the length. What is the area? Area is half of B by 2 into this distance, that is B by 2 tan theta. Tan theta becomes theta because theta is very small into dl over the tank. So this becomes equal to, if you see, 1 by 8, no, b square. I write theta here because tan theta is for small angle. Okay, this is the weight of it. Now our formula is going to be, we will go to the next diagram. But remember here what we have done, that there is a weight W, we have shifted it down to this W. That has caused my G, through which the weight of the ship is acting, to now shift to a new place which is G dash, what we call as G1. You see, this diagram I did not draw that. What happened is that earlier when I did not have this couple, I had my total weight of the ship acting through this point equal to W. Okay, now what I did is that I have added a weight here, or you can say added a force like upward and added a force downward. Basically, you have removed the weight from here, put it here. See, remove the weight from here, put it here. Let us say this distance is equal to, let me call it h here. So we know the formula that W into h must be W into GG1. Okay, now this W is, first of all, this W that we have found out is equal to integration of 1 by 8 b square theta into dl, or okay, dl. But how much is h? Now look at this thing. This is my tank here. This is my B here. Centroid of this is going to be 2/3 of that. This is another 2/3. 2/3 of B by 2, 2/3 of B by 2. So this makes it 2/3 of B, the full thing, here to here. So this H is equal to 2/3 of B. So I get here 2/3 of B. So this makes it here 1 by 12 of integration of B cube theta dl, or I can write it theta into 1 by 12 of B cube dl over the tank length. So how much is this quantity? Now this quantity is actually equal to IT of the tank. I will explain how it is so. You see, this again let me explain this. Now let us say this was my tank. I am drawing a cross section here view. Let us say that my tank was here. This is my tank. Okay, this length was tank length. Okay, see, and this was B. That's what we had taken. The B was the width of the tank. See, if you take a cross section here, you would have find that there is a shape here with a tank somewhere here to here. You know, because in between that, this was my tank. This is the cross section. Now, let us be clear. The tank was something like that with a width of B, with certain length. Okay, it has. I mean, this is a cross section view. If I cut it here, draw the section somewhere around this, you know, XX. This is a section at. You find this. Now you see here, 1 by 12 B cube dl integration. In fact, we are integrating that because it could be varying. It's a tank could be actually varying with. See, this is equal to the moment of inertia of the tank through its own centroid axis. Because by formula, moment of inertia of a tank, if you take any area, okay, any area, and if you take its centroid here, you see if you take moment of inertia about a line like that, you know, if this is equal to y, formula is 1 by 12 y cube dx over the length. This is actually I over the axis xx. But this is the formula of that ixx. If you have an area, if you have any area at all, and an axis going through its centroid, then the moment of inertia is 1 by 12 of breadth cube into dx. This is the formula. You see how it works is that you take this each strip here, take this, you know, as a box. We know the formula is 1 by 12 of cube of this into dx. Keep on adding them along the length. So what it means is that this part becomes equal to IT of tank. Normally we write this as IT small I to distinguish that it is for the tank, not for the ship. Otherwise we have some kind of confusion. Okay, so this is what we are writing it. So what we find out getting is that coming back to these formulas, that W into GG1, okay, equal to W into GG1, which we have done beforehand. Okay, in the again, if you we have done that before, and this is equal to, we found out IT into theta, but there are actually some more thing missing, because when we took this weight, there should be also rho of the liquid multiplied into G, because we took the volume. Remember that we took this volume of that only. Okay, we took this volume, weight actually volume into rho of the liquid into G. So this part has to be multiplied. You see, earlier what we did is that, okay, coming back to this, once more this previous part. See here, this W that I showed there, actually there should be also rho into G, rho of the liquid. You see, after all, this is the volume of that. See, 1 by 8 B square theta 2 by 3 B dl is the volume multiplied by GG1. Okay, it's a volume multiplied by GG1. The volume is half base into height, but the weight is going to be volume into rho into G, rho of the liquid, because it is that liquid that is shifted. Therefore, I have a low rho liquid, density of the liquid into G into the rest of the part. That part we did not at that time write because it gets cancelled out. So this becomes W. Now W is equal to rho of water into G into volume into GG1. Let me write it this way. So let me keep that here. So this gets cancelled out. Okay, then G to G1 turns out equal to uh, here rho of liquid by rho of water into IT by volume into theta. We have to now get back to the first diagram a little bit again and come back to that. Okay, so we note it here. Okay, now bringing it back, this diagram, G to G1, therefore this distance is what we found out. I will draw another diagram, but it is G to G1, that is what we found out now. G to G1 is equal to that number. Okay, let us maybe draw this again with respect to lines only, without any this thing. So we have got big one here, G was here. Now this was G0, my B was here, and B has gone down to somewhere, let's say B1. Let's say this is my angle theta, this is my M. See, this is how it was working, but G has now got shifted here to G1. That's what we have drawn earlier, you see. G or G0, actually some people are calling G0. So G0, G1, what I found out is I of the tank divided by volume, rho of the liquid by rho W into theta. The ratio of the density of the liquid with water, sometimes you can call that to be specific gravity of the liquid, although better not to call, since this can be salt water density. The moment of inertia of the tank divided by the volume of the ship. You see the unit, if you see, it will match, because this is meter 4, this is meter cube. So this is having same, so this comes to be meter. So it is exactly same, meter cube by meter, meter 4 by meter cube makes you meter. So it is consistent. Now let us see what happens. So the force is acting through this point. Earlier it was acting through this line. Now it is acting through this line. See, earlier it was acting through G0, and buoyancy was acting through this line, and I call that to be M. But now it is not the buoyancy. You see, by definition I am saying metacenter is equal to intersection of the buoyancy force with center line. Therefore metacenter is this only. We have not changed the metacenter. But effectively what happened, the weight is acting now through this point. Because when the weight acts through this point, see the righting lever is now this amount, because there is a weight acting, this going down. So righting lever now new if I call this to be GV, let me call this to be GV, becomes actually GV M into theta, again into theta because it's small angle. You see, earlier righting lever was G0 M into theta. So how much did the righting lever reduce? Obviously it is reduced by G0 GV into theta. Okay. In other words, it is as if my G has got up to this distance. You see, metacentric height. If I call this is my old metacentric height. Let me write down again. In terms of metacentric height. Earlier it was G0 to M. Okay, and therefore my righting lever was this into theta. Now with free surface it is GV to M. See here, this is my GV, this is M, and this is my G0. See, earlier my writing lever was this much. Now my writing lever becomes this much. Why? Because earlier my weight was acting through this, but now my weight is acting through this. See, this is exactly what has happened. As if the weight has, the CG has been shifted upwards as far as the weight is concerned. So when you shift weight up, obviously it turns out the metacentric height is reduced. How much? Clearly it will be reduced by the amount by which the G has been raised. Now you see how much is G0 Gv, if you see that now in terms of metacentric height. Now here we have found out that this diagram we should probably have to draw here. This is the case. This is the writing lever become like this. Okay. Now G0 Gv, okay, is or the new, let me put it this way, the new metacentric height is, let us bring the old diagram, then it will be easier. See here, this is what has happened, that my writing lever has become this, okay, this much. Now what we want to know is that what is my G0 Gv. Now you see G0 Gv, you can clearly see is nothing but G0 G1 into your G0, this thing, this G0 Gv into theta gives you G0 G1. See, this is my theta. Okay, or getting back to that, getting back to this diagram, G0 Gv. See, this is my G1 here, or maybe I should do in another clearer diagram because it is getting little much clearer diagram. Let me do it here, bigger one. So I had here G0, it has gone down to here G1, and this has become my Gv. Okay, this is my theta. So G0 G1 is G0 Gv into theta. Tan theta equal to theta again, because tan theta is theta, but this value is equal to, we have done that just now. Yeah, we have done this, equal to IT by V rho liquid by rho water into theta. So this become equal to G0 Gv into theta. So theta gets cancelled again. You cancel it because theta is not 0 but very close to 0. So G0 Gv becomes IT by V rho liquid by rho water, or reduction in Gm becomes G0 Gv is this value equal to this value. What is happened therefore, now we can consolidate this in this diagram, is that what happened earlier my G was through this, as if now my G is acting through a raised point. You see, as if G0 is raised to Gv. That's why we are calling it Gv, because you know this is like virtual G. So naturally Gm is reduced by that much amount. So the Gm, I mean when we say Gm, it is metacentric height, or this is the amount by which my this amount, this part is this amount. By this amount we have got a reduction of metacentric height. Or you see, it is possible that this G0 Gv may become more than G0 M. then this will cause the ship to become unstable, isn't it? Because what happened is it is as if you are raising the, see, the shifting of the weight is equivalent to as if raising the center weight, and if you raise it too much above, you can actually have a what you call instability. This is exactly what is meant by free surface effect, and why it is important, because we just see that the free surface effect is causing a reduction in metacentric height, and therefore it is actually dangerous situation. You know, a ship which is stable otherwise, as it you may start it off with a ship which is stable, full tank, and the little bit of liquid got consumed, it had a free surface, it might become unstable or close to instability. Okay, this is exactly very important. You will see that in all boats etc., whenever water, rainwater etc. comes in, there is always a pump. They are always pumping out, or somebody is draining out the water. You don't want to have a free surface in your boat. This is very common with fishermen's and country boats. There is continuously a pump. I have seen at least in some boats, maybe I will draw here, there is always a pump here like that is pumping out water, you know, in small country boats, the one that you pedal, because you don't want to have any free surface at all. It is always risky. So if you look at that, you will see that free surface reduction depends on this quantity IT for a given volume. Of course, it depends on liquid density. You know, lighter the liquid, okay, let me write it down. This reduction, some people call it GM loss, okay, is equal to, let me write it now this time opposite. On what it depends? If you look at that, see, raw water is of course more or less constant, because it is ship is going in water, not going to go in, you know, liquid. But you can carry sometime liquid other than water. Mostly actually you do carry, although you carry also water very much in a ballast tank. But many cases you carry oil, and in that case you will see that raw liquid is, if it is lighter, effect is less, because naturally lighter means less weight is being transferred. But it is quite often close to 1, 0.8, 0.9 oil, you know. Most significant parameter of course is this one, IT. For a given ship of given size, IT is the tank free surface area, causes maximum amount of loss. The example is like this. Supposing I have a ship here, we will just work this out now. There is a ship with a tank, full tank breadth here. So as it goes, the entire liquid goes like this. But now supposing you have divided the tank by a boundary here, then what would have happened? The liquid would have gone like this and it would have gone like this. See what happens, therefore you will see that this liquid shifting is actually less than this big triangle shifting. Before I go to this concept, because there are two tanks involved now, there are two tanks involved. Let us see what would happen to this term if there are two tanks. See, if there are two tanks, what is the IT? Another question that comes in, IT of which tank? Suppose most ships might have 10 tanks carrying liquid. Now IT is what? GM loss is IT by V. IT of which tank? That question comes in picture, like in this, when I am dividing in this two. Now it turns out that, see, that IT will become total GM loss is simply sum of IT of all the tanks. In other words, the total loss, if there are n tanks, becomes rho L by rho W into sigma IT, means summation of IT by V, I equal to 1 to n. That means if there are 10 tanks, you have to add the ITs up 1, 2, 3 like that. Why it is so? Let me see the physically why it is so. I will just explain that in a minute. But this is a formula, so that means we can always work it out. Okay, let us see why it is so. You see, now our formula was something like that. There was a ship here, then when I have a tank going like this, my G has shifted to this much. G1. But now if I, and this shift I have found out GG1 to be IT by V into rho, say rho liquid by rho water into theta. Now supposing there is another tank here, this will shift some more. So what will happen? This is going to shift to G2. Now G1, G2 is going to be IT of tank number 2 by this thing into rho liquid of tank number 2 into theta. This is tank number 1. So total shift becomes, if you see that, it will become rho liquid. Actually even rho liquid can be of tank number 1 by rho W, 1 by delta IT of tank number 1 plus IT of tank number 2. In fact, this rho can be taken properly. I mean, I am taking, in other words, basically what will happen is that total shift we can write it this way, 1 by rho water delta into IT into rho liquid of tank number 1 plus IT rho liquid of tank number 2, like that. First one is this by that, second one is this by that, third one is this by that, etc. Do you get my point here? See, so there is, it is a cumulative effect. You can add it up. Tank number 1, weight has shifted so much. Tank number 2, weight has shifted further so much. Tank number 3, weight has shifted further. Tank number 1, shift of weight has caused G to have moved up to this much. Tank number 2 has caused it to move further this much. 3 will cause further this much. So it gets added up all. So total effect of all the tanks would be, now each one again, this maybe this diagram actually requires a little bit of, let me draw a very big one so that we have no confusion. See, G is here, so it goes to the G1. How much is this distance? This distance is, this distance is 1 by rho W delta into IT of rho liquid of tank number 1. Because tank number 1 has, this is tank number 1. Now there is a tank number 2 here. That would cause, now begin with the G was here. So it is caught further raised G to G2. This much is going to be 1 by rho LW IT rho L of tank number 2. Now there is a tank number 3 here. Again this is also going to shift. We are going to give another this thing to G3. This is going to be 1 by rho L, rho W here, IT by rho L of tank number 3. So what is the total shift then? So G to G3 for example, or G to Gn, let me say, if there was n tank there, turns out to be 1 by rho water this thing into IT rho liquid of 1 plus IT rho liquid of n. You can add them up. That is equal to 1 by rho W this thing into sigma of IT into rho liquid I equal to 1 to n. Is the writing clear? I was supposed to write bigger. So this is what is happening. So therefore what I am trying to say is that this free surface loss can be added up cumulatively. It is not just one. You can simply add them one after other. Let us see now how this helps if I do a subdivision of tank to help reduction. Because we come back to this other diagram, because it is not necessary that it will basically gets 1/4. So I have got now this, let us say tank full width. Now my GM loss here, loss of GM. Now let us see that this breadth is equal to B. Loss of GM is going to be IT by V rho liquid by rho water, or it is, if I take one tank, it is proportional to obviously IT. What is IT? IT is proportional to B cube. Okay, IT is proportional to B cube because IT is proportional to B cube. Now let us say I have got a tank made here. I have put a tank here. Exactly halfway through. I have subdivided that by a tank. Then what would happen? What becomes to this? Now in this case, this is case 1. Now 2 tanks. What is happening is that now loss of GM is IT 1 into rho liquid, let me take constant, rho liquid 1 by rho W plus IT 2 by this thing. Okay. Now what is IT1? This is proportional to, actually I probably should not take proportionally, it is proportional to B by 2 cube. But there are 2 of them, so there is number 2 that comes in. So you see this 2 comes in actually, and that's sort of important. So basically that we end up getting here actually. No, let me look at this thing. Yeah, this becomes B cube by 4 times, okay, right. So you see that whatever was the loss in the previous case, my loss has been reduced by 1/4 time, or I can say B cube by 2 square times. Why it has happened? See, earlier case my liquid would have gone so much. You can actually make out this much of liquid was shifted out. But now my liquid shift out becomes this and this. These 2 together, that is this much of shift and this much of shift. These 2 together effectively the shift of G has become 1/4 time, not half, but 1/4 time. Okay. Square of n. Now we will find out that if you actually use n tanks, supposing I have taken n tanks, so you see n tanks, that means the ship I have got n number of tanks. Loss of GM proportional to B cube by n square. That means by subdividing the tank in n compartment, I can reduce the loss of GM by n square times smaller. You see if n equal to 2, loss of GM is reduced by 1/4. N equal to 3, loss of GM is reduced by 1/9. N equal to 4, loss of GM is by 1/16. Look at the advantage that we get. Let us see in a diagram. My G original was here, M was here. One tank, my loss was this much, my GV came. That means this much was my loss of GM. Supposing this was my loss of GM. This is important for us to realize. Let us say this is my loss of GM. Now I just subdivide, make it half. The loss would become 2, 3, 4, 5, just somewhere here. That means GV was with no subdivision, weight was acting through this. I just put one subdivision, as if the raise of G has come down to this point. So much. So earlier my GM was this much, now my GM is going to this much. I put one more tank, it will come down to 1/9. One more means here. In fact, if you take 1/16, almost no change here. Nobody does 1/16 though. 1/4 is good enough, because we have to remember that when you subdivide it, you actually have more subdivision means no holes and all. I mean, there is no manholes, it's just an independent tank. That means you have to have independent pipelines coming out through that, independent operation, etc. So you would not want to unnecessarily make more compartments. Not only that, you have a steel weight will go up because you have to have more structural material. Construction costs will also marginally go up because there is more material, more to construct. So you would not, in engineering design, want to put anything more than necessary ever. It turns out that if you make one subdivision, a longitudinal subdivision, it helps tremendously, very significantly. It helps the arresting of loss of stability. Okay, but now the question is, what is IT and which way I should subdivide. See, this is my ship here. So there are tanks here, all various, let's say it's the tanker itself, or let's say the ballast tanks are there here. The question is that we are saying where to subdivide. Shall I put a bulkhead here? What would happen? Now see the cross section of that. Say this is my tank cross section here. Now I had a bulkhead here. This is my tank number 1. This is my some tank. Now I want to subdivide. I did not yet say. So supposing I subdivide this way, is there any effect? The question is that I have to reduce IT about this axis. So if I actually subdivide here, my IT does not reduce at all, because IT is actually shift of weight this way. So the subdivision is only meaningful in this direction, longitudinal direction. So IT is reduced only, again you see this T and longitudinal is misnomer, it should have been IL. Actually this I is actually IXX, but we use IT because of transverse stability. Same thing. So that's why I always like to use IXX, because there is no confusion. So we can say IXX also. But the reason I am mentioning that, because most textbooks that you will open, you will find IT written there. So just so that you are sure, so it is IT reduced only on longitudinal eye of the vessel, eye of the tank. This is actually extremely important. So free surface reduction is very significantly affected by longitudinal subdivision. That is why almost all ships will have at least one longitudinal subdivision, a centerline bulkhead. All tanks would have at least that, you don't want to have anything less than that. Okay. So this is the question of free surface, which becomes sometimes very critical. You see how it can be critical. Let me also put here. Supposing the ship here, there are nowadays open hatch container ships coming up in some ideas, where the hatch is fully open, because you can put your very high, those ships must have very high freeboard, where you can directly put your cargo here, and there is no hatch covers to cover. Okay, then what happens? What is the danger? It may rain here, rainwater may collect here, and that will give a free surface large. So therefore, rules tells us that there must be certain pump of some capacity, so that the rainwater must be removed at certain rate. Otherwise, this will not be passed. Of course, you have a larger freeboard because of the safety, since water cannot go in. You cannot have this more than certain angle. Otherwise, liquid will go in and it cannot come out. That is why you have to have a large freeboard. But in addition to that, from our point of view right now, on free surface point of view, rainwater must be drained, but you cannot make a hole here like in a deck. So you have to have a pump. Similarly, on the deck, you have got this deck with this thing. You have to have this rainwater draining holes. Very essential, because rainwater accumulates, especially for small vessels, might cause some kind of your free surface effect. Earlier days, ships used to have a camber, and nowadays, of course, most people don't prefer, constructionally don't go for camber. But one of the reasons, there are several reasons. One was strength, but another reason was that it is automatically draining liquid out. So the full idea of when we are talking is that you do not want to allow unaccounted for liquid surface to form, like rain, etc., because you don't know the effect. For tanks, etc., that you have a free surface, you have to calculate the ship's stability with free surface. All calculation will be telling the GM uncorrected and then GM corrected for free surface. That you go to IRS, they will everywhere the calculation will have that GM uncorrected, GM corrected for free surface. So free surface correction has become, and this value must be more than some some number. Otherwise, the ship might become unstable. So this is the most important thing. See, I often wonder that in small boats, this last one, the small boats, sometimes people, ladies and all, sometimes may be carrying a lot of this small thing, bucket or whatever, with liquid. Now, when you come to the small boats, come to the getting down, suddenly you actually sometime may take on your head, like top. Now there are two dangers. First of all, the CG has gone up. Also the free surface. Both may actually cause sometime when you are in the port, the vessel to very badly behave. It is very dangerous thing. Because if everybody, while trying to get down on the shore, everybody gets up and takes them on head, then you have got dual effect coming in. Weight coming up, this free surface of course was there, but becomes more and becomes dangerous. These are the very few precautions. In fact, if small boat operators, we take care, we probably will not have such capsizing casualties as we have. So anyhow, we will stop this part of the lecture here. Okay, thank you.